So, when we were discussing about the various test procedures that we will be discussing for low temperature PG, I mentioned at the time that we will be looking into these 3 standards separately. So, the first one is ASTM D664, So, in the next 20-25 minutes we will be talking about the flexural creep stiffness of asphalt binder using the bending beam rheometer. Then in a separate session we will be talking about D6723 as well as D6816. Okay, so that is necessary for us to understand how the whole PG is written here. So, this is the standard. You can see that this was originally written in 2008 and it was reapproved in 2016, standard test method for determining the flexural creep stiffness of asphalt binder using the bending beam rheometer. It is normally designated as BBR. Okay. So, for us to understand and use this bending beam rheometer, we need to recap some of the elementary beam theory that we have studied in our mechanics of materials course. So, this is very familiar to all of you. So, what I have written here is a midspan deflection of an elastic prismatic beam of constant cross section when it is loaded in 3-point loading. PL cubed by 48 EI is well known to you. P is the load that is applied, L is the span length, E is the modulus, I is the moment of inertia. Now, what we do is we are going to rewrite this and write in terms of the moment of inertia also. If we take a rectangular prismatic beam of constant cross section at its midspan, one can take the above equation, rewrite to get PL cubed divided by 4 into B is the breadth, H is the depth times delta. So, this is what we are going to use here, and of course, the maximum bending strain, if we continue on the same way, you are going to get it as 6 delta H divided by L square. These are some of the derivations that all of us who went through an undergraduate civil engineering program would have already finished in our mechanics of material course. So, now comes the most important thing. Why are we now talking about elasticity theory when we very well know that the material that we are going to use is viscoelastic in nature? In fact, what we are going to do here as far as the low temperature is concerned is we take a beam something like this, we apply a load here and we find out how the beam is deflecting. Okay. Now, using this elasticity based formula, we compute two things. One is the midspan deflection, other is the stiffness, and using this length geometric properties, we find out what is the stiffness, and we also want to find out what will be the slope, whether the material will catastrophically crack. In fact, the idea of this low temperature PG is you take any material, you subject it to a very small load, see how it is sagging and when it is cracking. So, that means if we could find out what is the evolution of the stiffness, the deflection as well as the stiffness, we can clearly find out where is the maximum change that is happening, and it is more or less the point in which the beam is going to catastrophically crack. Okay, so that is the whole idea, right? But if we have to use it, we also need to be aware of the fact that even at minus 20 degrees centigrade, we are going to test the material can behave like a viscoelastic material. So, when we write all these things as part of the elasticity theory, how are we going to do it? So, here comes a very, very useful and important principle that is well explained in any textbook in viscoelasticity. What we can do is we use what is really called as the elastic viscoelastic correspondence principle. If you take a graduate level course on viscoelasticity, you will be taught this particular principle, in which we will take well known solutions in linearized elasticity and then we do a Laplace transform and try and find out what could be the equivalent solution in viscoelasticity. So, there are many criteria, constraints, conditions under which such transformation is possible, but since that is not part of this particular course, we will not be discussing all these issues here. So, what we are going to do is we need to be aware of the fact that in the linear regime, one can appeal to linearized elastic solution to linear viscoelasticity. So, what we will do is we will take the value E that was shown in the earlier one, what is really called as the flexural modulus, right. So, this particular E, and we are going to substitute it with 1 by d of t, and this is nothing but your creep compliance. If you recollect the material functions that we introduced in the earlier lectures on viscoelasticity, we introduced a creep compliance function, we introduced a stress relaxation function, all this on in time domain. In frequency domain, depending on whether we were controlling the stress or controlling the strain, we introduced g of omega, j of omega. In addition, we also introduced the phase angle function. These were all dependent on frequency here. There is also a popular way of designating d as compliance, it is nothing but j of t. So, this is a terminology that one should be familiar with, right. So, I can also substitute E in terms of what is really called as S of t, and we are going to call it as the flexural creep stiffness, okay, right. So, then what is this flexural creep stiffness? So, this is the formula, it is the same formula that we have used earlier, except that what we did, we made this as a function of time, we also made this as a function of time, and we designated this as S of t. Do not get confused with the phase angle for which we have been using delta. This delta is nothing but the midspan deflection. Such terminologies where the same symbol is used for to mean different things should become self evident as we are going through. So, we are not really talking about the phase angle, we are only talking about the midspan deflection, okay, right. So, it is given here as PL cubed divided by 4 into BH cube times delta t, and this is the deflection of a beam at a time t, okay. And please understand this delta of t as well as S of t indicate that the deflection and stiffness are functions of time, okay, right. So, let us go to the next thing. So, how is this actually this test is carried out? You can actually see that there is graph 1, this top one, in which a load is applied. This load consists of two parts, there is a contact load, okay, and there is also a test load, and there is something called as a seating load. So, if you look at the seating load, it is the same as the test load. So, as per the procedure, what we do is we load the sample in 3-point bending, we apply a seating load, and then immediately what we do, we release the seating load and bring it such that the remaining load, that will be the contact load, will be there, and wait for 20 seconds, and then we apply the test load. This duration can be is based on whatever is the specification that you want. So, this experiment consists of just applying a constant load and trying to see how the deformation is increasing. Please understand, I will also be reiterating it later, there will not be any recovery in this test. We will be just loading it and see how the deformation keeps increasing. So, please do not get misled by whatever is mentioned in D6648. Okay. So, this is going to be the deflection, this is taken as the 0 time, and this is how the deformation is going to increase. Okay. So, the first and foremost thing is apply a constant test load of this much for 240 seconds, and we will collect the midpoint deflection of the test specimen at some select time interval, and I have made this slightly different. We will know what it is, 120 second and 240 second. Now, what is the temperature at which we should be doing this test? We will be doing this test at the PG low temperature. In fact, what we want to do is whether the bitumen that we are going to use will be able to withstand the low temperature conditions prevailing in any geographical location, correct. So, we will be testing it at the PG low temperature. So, how does the output looks like? So, we will use the deflection here, collect the midpoint deflection, then use this formula, okay, because we know what is the load that is applied, we know what is the span length, we know what is the width of the beam, we know what is the depth of the beam, and this is the information that we collect from the test. Substitute this and we are going to get this particular graph. Okay. So, we will get the creep stiffness and we plot log of creep stiffness versus log of loading time, and the slope of the response that is called as the m value is used as a specification parameter. So, how do we do it? First and foremost thing is, what we will do is, we will first, we have to curve fit this stiffness that you are seeing here in a, we are going to basically we are going to use a high second order polynomial and we fit this now. So, because we need to really find out what is the stiffness, this particular slope value that we want to do. So, for that we have to curve fit this whole thing, and there is a procedure that is presented in the ASTM standard. You can take a look at it, more or less it looks like this, right. So, you take this data, fit it to this equation, find out A, B and C, and then using this you evaluate what is really called as the m of t. M of t is nothing but d log s of t divided by d log t. So, you do that and you get the m value. Now, what this particular value, the stiffness value means is, if I take it from the specification, it says the maximum value of the stiffness should not exceed 300 MPa. Of course, these correspond to the temperature in degree C. So, that means if I use any PG for which the low temperature is, let us say minus 12, at minus 12 the maximum stiffness should not exceed 300 MPa. In addition, the minimum value m that you see here is 0.3. Now, where should I evaluate this MC? Because I need to substitute some value of t here. I will know how to find out B and C from this expression, but what do I do for t, and that is what I have underlined here. So, I will collect the midpoint deflection, and at 60 seconds I will compute, in fact you can actually see 60 seconds here, I will compute the m value, and that is the value that should be 0.3. So, this is the spec that one need to use, right. Okay. So, now we can use this standard for unaged, short term aged as well as long term aged, and it is also very clear that we can use this for only for in the, if the flexural creep stiffness is in the range of 20 megapascal to 1 gigapascal, and the test specimen, it should not deflection more than 4 mm, or it should not be less than 0.08 mm. It should not exceed 4 mm, it should not be less than 0.08 mm, and we do not do any recovery measurement here. Okay. So, this more or less completes our discussion that we wanted to have as far as D6648 is concerned. We will complete this lecture on the performance grade for bitumen by looking at the low temperature PG, and in fact, in the earlier lecture we talked about the bending beam rheometer, and right now what we are going to do is to talk about the direct tension test, and then we will also try and see how we could use this information to make some statement about the low temperature performance grade properties of asphalt binders. Okay. So, this is the ASTM standard ASTM T6723 that specifies the standard test method for determining the fracture properties of asphalt binders in the direct tension mode. So, there are few definitions that we need to understand before we start talking about this, and these specific definitions are applicable only for the case of bituminous binders tested in the direct tension mode. So, they are very specific, because the definitions that are given can also be very generic, in which case some of the phrases that are used may not directly be applicable for all the materials. Okay. So, the first and foremost failure mode is brittle. So, the type of failure where the stress strain curve is essentially linear up to the point of failure, and the failure is sudden without appreciable reduction in the cross section of the specimen. So, in fact, the important phrases related to this are underlined by me here. You need to understand something about the linearity here. You can have a brittle fracture which is not necessarily linear, but as far as this particular standard is concerned, this is what is really assumed. The second failure mode that is discussed here is the ductile, a type of failure in a direct tension test where the specimen does not rupture at all, but fails by flow at a large strain. Not very clear what flow means, not very clear what large strain means, but you need to visualize this more about trying to do a direct tension test in which the sample failure is not instantaneous, but rather it just keeps elongating, the sample keeps elongating, right. Now, we look at the brittle ductile mode, the type of failure where the stress strain curve is curvilinear. Please take a look at this specific word, and the failure is by sudden rupture, limited reduction in the cross section of the specimen occurs before rupture. Okay. So, what we normally do in this particular test is you can actually look at the cross section of the sample. So, this is the typical sample that is made. Making the sample is a very tedious process, but nevertheless if you really want to test the low temperature performance grade properties of the bitumen, you need to do this. Particularly the ASTM 6723 has detailed procedures on how the sample has to be made. So, then this is applicable for the case where you can use the sample in the unaged condition, short term aged condition, or long term aged material, and the temperature in which you will be testing is somewhere between 6 to minus 36 degrees centigrade, and if your binder is having particulate material that is having dimensions more than 250 microns, you may not want to use this particular test. For instance, you could be testing a mastic which will have some binders, some particulate matter filler material more than 200 micron or 300 microns. Sometimes it is possible that you could also have rubber modified binders in which some of the rubber particles may be having sizes more than this, in which case this test will not really be applicable. And the failure mode that is permitted is brittle or brittle ductile, and not definitely the ductile mode. So, what do we do here in this test? It is a fairly straightforward test. You keep the sample at the specific temperature that you want to test for, and subject the sample to a constant rate of elongation. So, that means you try to pull it at 1 mm per minute, and the data acquisition system that is applied as part of the equipment will record not only the elongation as well as the load that is necessary for you to subject the material to that constant displacement rate, and the stress and strain when the load reaches the maximum are recorded here. Okay. So, coming back to this is the sample now. So, this is the stress that you are really looking at, and this is the strain that you are looking at. So, when you plot the stress versus strain, this particular point is taken as the failure load. The sample, the original undeformed sample and the deformed sample, when it is subjected to a specific load that will result in a constant displacement rate, is given here. Okay. So, these are some of the equipments. There are many equipments that are available. These are some of the equipments that are available for doing it, and in fact, you can actually see a direct tension test sample here. Okay. And what is the failure mode here now? As far as the PG is concerned, the failure strain. So, if the failure strain is minimum 1%, find out the temperature at which the failure strain is minimum 1% at 1 mm per minute when it is subjected to this loading condition. This is the low temperature PG of this material. So, this is how the test has to be interpreted now. Now, we come to the very last one, which is the low temperature PG of the material. This is actually a lot more complicated than whatever we have discussed till now, because if you actually think about it, you have carried out two types of tests. One is a bending beam rheometer and other is the direct tension test. Can we use the information from both the tests to come out with a low temperature performance grade of the material? Okay. So, that is the whole idea for this particular standard, because whatever we have discussed till now for the high temperature performance grade or the intermediate temperature performance grade had some connection whatsoever with the performance of the binder in the field. So, that means when you use a G star by sin delta of 2.2 kilopascal, there is a relation between the rutting rate or the expected rutting in the field. When we are talking about G star times sin delta of 3000 kilopascal in the olden standard or 5000 kilopascal in the new standard, again there is a connection with what is the critical strain, what is the onset of fatigue damage. But when it comes to the low temperature performance grade, the connection whatsoever between the field behavior as well as the lab testing is somehow that is missing. So, let us see how to establish that. So, it is very much necessary to read through the section 4.1 that is given as part of this test. It says basically that the practice describes the procedure used to calculate the relaxation modulus master curve and subsequently the thermally induced stress curve for an asphalt binder from the data that is generated from the BBR. So, what you are going to do is you will find out the critical cracking temperature for a typical asphalt binder based on the determination of the temperature where the asphalt binder's strength equals its thermal stress. Okay. Now, let us sit down and understand this little more carefully. How do we use these two standards 6648 as well as 6723 to calculate the low temperature properties of the binder, and how do we really compute the low temperature PG of the binder? We need to understand that the direct tension test is a truly displacement controlled test, okay, and the bending beam rheometer is truly a load controlled test. So, now what we really do here is the following: you use the bending beam rheometer, and using the bending beam rheometer, what will we get? We will get the compliance, because you are applying the load and you get the strain per unit stress, you will get it. Now, then what we do is we invert the compliance to get the stiffness, and we compute the stiffness master curve, and for that we typically do it at two temperatures. Okay. and now when we do this, we have to ensure that we are in the linear regime. Okay. Only then you can even define behaviors, material properties such as compliance. Number 2 is, for you to do the time temperature superposition principle, there are many things that you should restrict to. For instance, you really need to measure these things in the linear regime, you should not be measuring it in the transitory regime. Then whether you are using an Arrhenius type shift factor or the William-Landau-Ferry shift factor or a sigmoidal type or a shift factor of the polynomial type. So, all those things needs to be clarified. So, once we measure the compliance, then when we do the find out the stiffness master curve, then what we are going to do is, if you get a stiffness master curve, we need to convert the stiffness master curve to tensile relaxation modulus master curve. So, some kind of a transformation should happen here. So, it is not straightforward to flip between a stiffness master curve to the relaxation modulus master curve. Why? Relaxation modulus is basically defined in a specific way, stiffness master curve is defined in a completely different way. And once it is done, then we can actually compute the thermal stresses. We will not be getting into the details related to how these thermal stresses will be computed, and then these thermal stresses will be compared with the failure stress from the direct tension test. So, what we are doing is, you do the bending beam rheometer test, you analyze the test results, and then you compute the thermal stresses, and then you compare it with what we are getting at the direct tension test. So, this also needs, there are few additional factors that are used to convert the stresses, the thermal stresses that you measure in the laboratory for the specimen to the field thermal stresses. So, there are some what you would say as some additional factors, empirical factors that are used, for which substantial amount of data is needed. So, let us recap and understand this. As we go down to the low temperature, two types of tests are prescribed for low temperature PG. One is a bending beam rheometer, in which you apply a load and measure the creep compliance as well as the slope of the compliance equation, compliance curve. Then you use it in your PG, okay, that is one side. On the another side, what you do is, you take a sample and then subject it to a constant displacement rate, find out the load point at which it fails. The first test is a non-destructive test, the second test is a destructive test. So, that is why you use the first test, find out the material properties, and then that is the thermal stresses that you can actually compute, and these thermal stresses that you compute using the bending beam rheometer in essence should always be comparable to the failure stresses that you are going to get from the direct tension test. So, that means the limit is the failure stress that you are going to get in the direct tension test, and that should never be exceeded based on the thermal stresses that you are going to get from the bending beam rheometer. Substantial amount of work is needed before we could take it for practical implementation. So, with this slide, we are actually at slide number 100, we finish our discussion on the performance grade for bitumen. Thank you.